Students, welcome to the third part of second module in compressible fluid flow. So students, this module mainly deals with the isotropic flow, as we have already discussed. Actually, in the previous session, we have learned the effect of area variation on the flow, right? So how the area variation acts or help in expanding or compressing the flow. I mean, sometimes the converging. Actually, what was the conclusions at we reach? A diverging passage can decelerate a subsonic flow towards zero velocity, right? And it can accelerate a supersonic flow towards maximum speed, right? And a converging passage can accelerate a subsonic flow. At the same time, a converging passage can decelerate a supersonic flow, right? So we have discussed converging diverging passage, right? A converging diverging passage, the Mach number may become unity over the area of passage is minimum. So we have discussed a converging diverging. So you have to show this insulation, otherwise this flow won't be a isentropic flow. Okay, so students, when this m is less than 1 subsonic flow, the flow get decelerated and sorry, the when m is less than 1, the flow get accelerated and its velocity becomes equal to that of a at here. So here m will become 1, and after that, since the passage is diverging means it will act as a nozzle again, and the Mach number will become 1 here, right? So students, so here this acts as a nozzle. A converging diverging passage act as a nozzle if at inlet Mach number is less than 1. So similarly, but the same converging diverging passage can act as a diffuser if m greater than 1. So this is a diffuser, right? And this is a nozzle. So what determines whether it is a nozzle or whether the passage act as nozzle or a diffuser? So the Mach number at the entry, right? Mach number at the entry. So here, since it acts as diffuser, its velocity gets reduced, and at some section m will become 1. So that will be the minimum area section, and m will become 1 here, and after that m will be velocity again decreases because it is a diffuser. Pressure increases, velocity decreases. Velocity increases means Mach number will become less than 1. So this is a converging diverging passage. So a diverging passage may either be an accelerate a subsonic flow or decelerate a supersonic flow. Okay, it depends upon the Mach number at the end. So let us consider a converging diverging passage acting as a nozzle or diffuser. So it can act as whether nozzle or diffuser depending upon the Mach number of the flow entering the passage, right? So in both cases, at the minimum area called the throat. So this minimum area, so this area is called throat. Throat of the passage, throat of that, whether it is nozzle or diffuser. So minimum area at throat area will be minimum. So in that passage, that particular section where area is minimum is called throat of that passage. Okay. So the important thing you have to note that is at throat, what will be the Mach number? Mach number will be what? Mach number becomes unity at throat in case of an isentropic flow. Okay. So the largest Mach number that can occur at the throat is unity, right? So maximum possible Mach number, that is maximum possible Mach number at throat is unity. The value is 1. So in the case of a nozzle, if the mass flow rate is low, so students, if mass flow rate is a little bit low, okay, so then the Mach number at throat can be less than sometimes Mach number at throat Mach number at throat will be less than 1. So students, you have to note that usually Mach number is equal to 1. The maximum possible value of Mach number at throat is 1, right? So sometimes due to some decrease in flow rate, Mach number at throat may be less than can be less than 1. So keeping the entire flow subsonic. So since the flow remains subsonic at throat, so students, let us students, if at throat m is still less than 1, because due to the decrease in, or due to some reasons, if the flow rate is lesser value, the Mach number at throat may be less than 1. So if Mach number is less than 1 at throat, it means the flow is still subsonic. So if the flow is still subsonic, if you consider this particular section at the end, so this is the diverging section, right? So diverging section, if the value or the Mach number of the flow at the end of a diverging passage is less than 1, means it acts as what? It acts as a diffuser, right? A diffuser always decelerates the flow, right? A diffuser always decelerates the flow. So since so the flow will remain as subsonic itself. It won't get accelerated. So this won't happen. M will not be greater than 1. M will remain as M's values will be remained as less than 1 itself. So it means the flow is still subsonic, right? So since the flow remains subsonic at throat, the divergent region has to act as a diffuser. So flow remains subsonic at throat, right? So if a throat is the entry point of that diverging section. So at the throat, the flow remains subsonic, means the diverging section acts as a diffuser, right? Thus, diverging section act as a diffuser, right, and not as a nozzle. So actually a diverging section acts as nozzle in a hole, right? So but in this case, when the flow is less, first part is nozzle, the second part becomes diffuser. So such a device is known as Venturi. Such a device is known as Venturi. If first part is nozzle and second part is diffuser, means it acts as Venturi. So students, have you heard about Venturi meter? So you know the shape of the Venturi meter, right? So Venturi meter consists of first a converging part, a throat, and diverging part, right? So the divergent, if the mass flow is sufficiently high, then the Mach number at throat becomes unity and the device can act as nozzle. But if the Mach number is not that high, the whole device will act as a Venturi. So Venturi always keeps the flow. If Venturi will be acting, Venturi will keep the flow as subsonic itself, right? So it won't accelerate the flow. The students, we know Venturi meter won't accelerate the flow, but a convergent divergent nozzle should accelerate the flow. So there is a difference between Venturi and nozzle, even though their shapes are same, even though the shape of nozzle, a convergent divergent nozzle and a Venturi is essentially same. But what make it different? What make it different? In nozzle at throat, Mach number will be 1. In Venturi, Mach at throat will be less than 1. How Mach at throat becomes less than 1? If the mass flow rate is sufficiently low. Mach here m throat equal to 1. If the Mach number reaches 1 at throat area, it will act as nozzle. So it can be concluded that when the Mach number reaches unity at the minimum area, the device allows the maximum mass it can pass. At this condition, the flow is said to be choking. So this is the phenomena that we are essentially going to learn in this session. So what is choking? Choking means reaching the Mach number. So the phenomena of reaching Mach number's value to unity at a minimum area throat. So when Mach number reaches unity at a minimum area or throat, then the flow is said to be choked. So this phenomenon is called choking. So in Venturi, there won't be any choking because Venturi converge at the throat, Mach number will never reach 1. But in our convergent divergent nozzle, choking will definitely takes place. So choked flow represents the maximum flow rate for a given set of initial conditions that can pass through a given tube. So students, you have to note down that if choking takes place, the device allows the maximum mass it can pass. That is, mass flow rate is maximum. In Venturi meter, mass flow rate won't be maximum. So that is the difference. Okay. So I will show you a figure. So this is first figure. This figure represents. So students, I'm showing you two type of nozzle. What's the difference here? So the same convergent two type of convergent divergent sections. Okay. So students, in the first case, so this is the reservoir. So reservoir is having the same condition of the stagnation condition. Velocity equals 0, P is P0, stagnation pressure. T will be T0, rho will be rho 0, H will be 0. Same case here. But what is the difference? The velocity at the entry is same, m less than 1. That is, a Mach number is same, subsonic flow. But what is the difference? Here at throat, the minimum area, Mach number reaches 1, but here it remains empty less than 1. So if empty is equal to 1, then after that section the flow will become supersonic. But if empty less than the Mach number remains less than 1 at throat, then after that flow will be subsonic itself. So that is the difference. So here this will be a nozzle, this will be a Venturi. Okay, so what will be the Flow parameters at the throat. At throat means star value. So at throat, 80 area at 80 will be A star because it is critical. Because at critical section means the Mach number equal to what? Critical conditions. So, but here what will be 80 will be 80 should be greater than A star. Then only the flow or the choking won't take place. The choking shouldn't take place. Then only it acts as an injury. So the choking should not take place means the flow rate hasn't reached that maximum value. Flow rate hasn't reached the maximum value means the throat area is even bigger than the critical condition. That is why 80 should be greater than S star. Okay. Similarly, here Pt will be equal to P star whole value. V star equal to A star. But here Pt will be greater than P star. Right? Vt will be greater than A star. So that is the difference between flow parameters at the throat for nozzle and venturi. So students, important thing is to learn the concept called choke. Choke means reaching the maximum value of mass flow rate at the minimum area. So choking takes place in the case of nozzle, but never takes place in the case of venturi. If choking takes place in venturi means it is no longer venturi, it will act as a nozzle. Okay. So students, now we will go to learn a property ratios in case of isentropic flow, in property ratios in terms of Mach number. So we are going to learn some equations. So students, we have already learned the relation between stagnation temperature, pressure and density with the corresponding static temperature, pressure and density. So they same equations we can apply here because stagnation condition, that concept, because in stagnation condition it was isentropic flow, it was based on isentropic flow, right? So here we are considering isentropic process. So the same equations are applicable here also. Students, hope you have learned these equations. T0 by equal to some t into 1 plus gamma minus 1 by 2 max square, right? Similarly, P0 equal to P into 1 plus gamma minus 1 by 2 max square into raised to gamma by gamma minus 1. Similarly, rho 0 equal to rho into 1 plus gamma minus 1 by 2 max square into 1 by gamma minus 1. All these equations you have already learned in your first module, right? So the same equations are applicable in case of isentropic flow also, because so here what is T0, P0 and gamma 0? So T0, P0 and rho 0 are nothing but stagnation. They are the stagnation properties or properties at reservoirs. Properties at reservoir, right? Reservoir means the place where the location where velocity is 0. So that is T0, P0 and rho 0, right? So if you know the Mach number at a particular section and any one of the static or stagnation condition, you can find the other. If you know the stagnation condition, you can calculate static. If you know the static, you can calculate stagnation, right? So students, if you put m equal to 1 here, then t will become t star, right? M equal to 1, right? So t will become t star means the critical value. So the equation will become like t0 equal to t star into 1 plus gamma minus 1 by 2, right? So I'm putting Mach number as 1, then the equation will change to this form. So T star by T0 equal to, I think you take 2 here, 2 plus gamma minus 1 by whole 2. So it will become 2 by gamma plus 1. So the equation will change to this form, 2 by gamma plus 1. So similarly P star by P0 will become same, 2 by gamma plus 1 raised to gamma by gamma minus 1. Similarly rho star by rho 0 will become 2 by gamma plus 1 by gamma minus 1. So this is the relationship between stagnation properties and critical properties. So if gamma is taken as 1.4, because for air gamma is 1.4, right? So in the case of so you can substitute gamma equal to 1.4 here and here also. So all these values you put gamma equal to 1.4, then you will get T star by T0 will become 0.833. Similarly, P star by P0 will become 0.5283 and rho star by rho 0 will become 0.6339. So in case of isotropic flow, you will get some property ratios at the critical section. Like temperature ratio will be 0.833, pressure ratio 0.5283 and density ratio 0.6339. So these are dimensionless ratio. Okay, students, if you have to get the dimensionless ratio represent the critical properties, you can combine. So like you need to get an expression for T star by T. Actually now already we have got the various. Okay, here you have the relation between T0, T0 and a T, P0 and P. So this is T0 and T, T0 and T, P0 and P, and rho 0 and rho. And you have T0 and T star, P0 and P star, and rho 0 and rho star. Now if you need a relation between T star and T, P star and P, and rho star and rho, you have to combine both the set of equation we have derived earlier. You will get it as how to. So T star by T is nothing but T star by T0 into T0 by T. So you just multiply. You have both this equation. Where so T star by T0 is there, right? And T0 by T is there, right? So combine both the equation, you will get it will 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 max square. So similarly, P star by, you just try on your own, P star by P equal to 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 max square gamma by gamma minus 1. Similarly, rho star by rho star by rho is equal to 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 max square into 1 by gamma minus 1. So only difference is in the uh, power. Okay, power of the equation. So now we are going to learn the area ratio in terms of as a function of mass, as a function of Mach, or in terms of Mach number. Okay, so students, you know rho AV equal to constant, right? So it can also be written as rho star into A star into V star, because rho AV is constant at any section. So I have written a section on the critical section, the property based on critical section. So students, you can write A by A star equal to rho star by rho into V star by V. Right? Right? So students, now you know what is V star by V? What is V star by V? What is V by V star? Actually, V by V star is nothing but Mach star or reference Mach number, right? So you have already derived the equation for Mach star in your previous module as root gamma plus 1 by 2 Mach square by root 1 plus gamma minus 1 by 2 Mach square, something like this. So I think you remember this equation. So if you don't remember, you just flip back to your earlier videos or notes. So Mach star can be written like this. Now actually here we require V star by V. So V star by V is 1 by Mach star. So it will be like 1 plus gamma minus 1 by 2 Mach square by gamma plus 1 by 2 Mach square. So if you can take this Mach star outside, so it will be 1 by outside the root 1 by root 1 by m into root 1 plus gamma minus 1 by 2 Mach square by gamma plus 1 by 2. So you divide gamma plus 1 by 2 for both these terms. So you will get 1 by Mach star equal to 1 by m into 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 Mach square into whole root. Whole root means you just put half, raised to half. So students, now here this is nothing but what? This is nothing but V star by V, right? V star by V. But here V star by V is now available already. Now what is rho star by rho? Rho star by rho, we have derived the equation for rho star by rho in the just previous slide, right? So it is nothing but 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 Mach square. We substitute these equations here, so you can get A by A star as after substitution you will get A by A star as 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 Mach square 1 by gamma minus 1 into what? 1 by m into 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 Mach square half, right? So both these terms are equal, only the power is different. So you can simplify it as 1 by m 2 by gamma plus 1 plus gamma minus 1 by gamma plus 1 Mach square. So this power plus this power, what is that? Half plus 1 by gamma minus 1. Or you can simplify it as if you add it, you will get gamma plus 1 by 2 gamma minus 1. So this is the equation for A by A star. So the variation of area ratio with Mach number in variable area isotropic flow is according to this particular equation. So this can be shown in a graph like this. A by A star in the y-axis, Mach in the x-axis. So you can draw this graph. So according to if you plot that equation for different Mach number, you can get it as like this. so just note it down. So this base point, so this point will be okay, so here m equal to 1, here it will be m greater than 1, here it will be m less than 1. Okay, so to this direction supersonic, this direction subsonic. So this will be the variation of area ratio with Mach number. Okay. So students, with this particular concept or topic, I think I'll stop this particular session. So we'll continue in the next session. Thank you.